Okay, so let us begin. Um, if you want to ask any question, I think you can send me a chat message through this. Um, I presume you can hear me. Um, I guess since you're all muted, you cannot tell me. Maybe one of you can unmute and tell me that you're able to hear me. Okay. Can one of you tell me that you can hear me?
Oh, we can hear you.
Okay, very good, Shreya. That's good. All right, I need a bit of feedback. It's hard for me to have absolutely no feedback, and I don't
Yeah.
know whether you're able to get the message or not. All right, so we are into chapter 12 of the deep learning course. A little bit of logistics. I got a message from the dean of the electrical sciences that they are contemplating on reopening the institute only on June 1st for the academic curriculum, which means we lose a solid 2 months, April and May. And then we begin as if nothing happened. So we just restart where we stopped, and they will allow for 1 month for the semester to wrap up, and that will so that everything will be wrapped up by the end of June, by July 1st. I'm thinking that we can go along with these online lectures and so on, so that that gives us a solid 2 months. Hopefully, we'll perfect this technology of how to have these lectures, and you will also have the slides and all that, so that we really don't need a full month after we begin on June 1st. Maybe we can wrap it up within the first week of June, and we would have covered all the material, and we could have a final exam in the first week of June. This is what I'm thinking right now. Anyway, we got 2 months to go. So, and there can't be the kind of quizzes that we had and so on. So we'll just wrap it up in that way. So that's why we are headed. And so I am recording this video also. So those who could not join can also hear the video, but you got all the slides also. So that should make it easier to know what is being covered. Okay. All right. With that preamble, we'll begin. So we are into chapter 12 of deep learning. We have finished all the basics of the current methods of deep learning. And after we look at the applications, we move on to research topics in deep learning. And within applications, we've already spent a couple of weeks. We spent a little time on computer vision application, and that's usually the standard application accompanying much of deep learning. We did some of that, and we also introduced the knowledge-based systems. That's a topic which is one of the uh, later topics, but I wanted to cover it early. And we covered the knowledge graphs and knowledge-based system application. And the most important application, in my opinion, today in deep learning is natural language processing. And that's what I'm going to begin today, how deep learning methods are used in natural language processing. And we'll spend today, we'll go for 1 hour today. This is a trial till about noon. And then we'll pick up again on Wednesday at 11 o'clock. And so today's lecture and Wednesday's lecture will both be on natural language processing. There is one more application after this, which would be recommendation systems, which is not as large a topic as this one is. Natural language processing merits a full course on its own. Actually, my wife Rohini teaches a full 1 semester course on natural language processing. And we are, of course, covering it here as natural language processing application of deep learning. And a course on natural language processing would typically cover the classical methods also, the syntactic and semantics and things like that, the classic approaches. But what has happened even there is the deep learning approaches have taken over almost completely. So that is becoming an entire course on natural language processing using deep learning. So anyway, we're going to have a 2-week version of a full semester's worth of course. It's quite an exciting and interesting topic. And so these are like the major applications of deep learning. There are also others one could look at, like, deep learning for scientific discovery is another one. That's a very interesting emerging topic. How can deep learning do science for us? And of course, the amount of material there is not so different. So if it is a classic method, you're going to be using linear regression, logistic regression, various other ensemble methods and things like that. Then of course you just need to know the basic techniques. You can apply it to whatever problem, you can formulate it like that. What is different about natural language processing is that some of these topics are very oriented only towards language. And we study it primarily for the purpose of natural language and not as a general technique that could be used for anything else. All right, so that is the beginning point. And because this is a huge topic, there are a lot of subtopics here. Let me see if I can move on to the next slide, which kind of gives you an overview of many of these topics. So we begin with this overview: what is natural language processing, which is this set of slides here. And after we finish that, we go into one classic method called N-gram models would be the second topic. And what is this N-gram models? It's about frequencies of combinations of words. So those are called N-grams. N-grams can be like bigrams, trigrams. These are like two words at a time, and unigrams are one word at a time. How often does a word occur? Bigrams is how often do pairs of words occur, and trigrams, how many triples of words occur, and so on. Why do we want to know all these kinds of things, like how often they occur? Is what we are headed here into are what are called as probabilistic models. So natural language processing has become a whole play of probability. That is, we look at what's the probability of this word, what is the probability of this set of words, that kind of a thing. And we'll begin by saying, why do we need probability to understand language? So we begin like that, and we introduce N-gram as a simple way of doing it. And then we begin by saying, okay, N-gram is a good way to do it, but it is limited. Simply looking at frequencies may not do a great job on understanding what is being said. And so we get into neural language models. The word neural is because it's based on neural networks, which is what deep learning is about. And then we move on to a topic called high dimensional outputs. This is because the number of possible words in any language is quite large, maybe 10,000 words or 100,000 words, that kind of thing. So if you're talking about machine translation or generating language, we're talking about which word can it be? There are 10,000 possible words for each word, or 100,000 possible words. That's a very high dimensional output. And in classic deep learning, if, for example, in supervised learning, we have discussed, okay, cat or dog or so on, and the number of classes tend to be not that large, maybe 10 classes for digits, and maybe 100 classes, maybe even 1,000 classes for some of the larger data sets. Here we're talking about high dimensional output of much larger, 10,000, or it could be 100,000, and so on. And so then we get into another topic, combining neural language models with N-grams. So then that's an idea of classifier combination or ensemble methods can both be combined together. And we talk about neural machine translation as a topic. Actually, what happens is this particular slide needs to be updated a bit. Within neural machine translation comes a huge topic called attention models. And attention models was a small subtopic within neural machine translation, but it has dominated all of NLP today is these attention models. They're doing spectacular things, and attention models also are pertinent now to computer vision as well. So I have almost a full lecture. Maybe we're going to need 3 lectures for covering NLP, and attention models are going to take up quite a bit of our discussion there. So that is this section 5, neural machine translation, is a very big topic. Although it starts with translation, it's really about how do we get these neural networks to focus their attention on something specifically, uh, and then finally the historical perspective. So this is what is to come in natural language processing. So we'll begin now with what is natural language processing, and the immediate next thing is why do we need probability to deal with natural language? Okay, so what is NLP? NLP is natural language processing, and this is about computers to process languages that are ambiguous. We are very familiar with computers that process unambiguous languages. So, C++ or Python, they're unambiguous languages. There is an unambiguous parsing of the program, saying what is this program about, and it should be executed as it is stated. So those are unambiguous. But naturally occurring human languages, like such as English or Hindi or Kannada or whichever language, are ambiguous, and they defy formal categorical description. You can't say this is exactly the syntax that's being used. There is a lot of variations here. And natural language processing includes machine translation, and where a learner would read a sentence in a language and emits a sequence in another, maybe English to French or English to German, or German to English, and so on. And natural language processing is based on language models. So, like such as machine translation, they are based on what are called as language models. So, the modeled language. And what do we mean by a language model? It typically involves defining a probability distribution. Probability comes into play here. So to be able to process ambiguous languages, we need to work with probabilistic models, and they are defined over sequences of words, characters, or bytes of natural language. So then we have to ask the question: to process ambiguous languages, why do we need probability? And so this is the slide which says, so why do you use probability in NLP? And we first talk about how natural language is ambiguous. Why is because its use is situated in a world context. We're talking about a lot of context playing a role in whatever we're talking about. We also tend to say little that is needed to be understood. Assuming most of us like to talk, essentially we're trying to communicate, and we don't try and give a lot of preamble and explanation. Of course, some people do that, maybe talk too much, as we say, but most of us are communicating with as few words as possible. We want to communicate. And so we only have that much information that is being given. So we have to process it with a lot of context that is around. And the tasks that we do involve reasoning about meaning, and using word knowledge, not in the source text. So it is not simply a matter of taking this one word or one sentence and translating it, because there's a lot involved in knowing what is the context in which it is being said. And we end up wanting to move to quantitative techniques, which move away from unrealistic categorical assumptions of earlier formal linguistic theory. That particular sentence is a criticism of classic natural language processing, which has been a field of computer science ever since even when I was a graduate student many decades ago. Actually, my own master's thesis done many decades ago was about natural language processing to answer questions about sports and things like that. I did a project like that. And we used simple ideas about keywords and things like that. So those kinds of things only take you so far. And so this says we need to do much more than that. And again, motivating the use of probability. And so models that assign probabilities to sequences of words are called language models or LMs or language. Okay, we call them abbreviated as LMs. Okay, here is another example which I found, which was probability in machine translation. Here is a sentence in the Chinese language, and literally, if it is translated letter by letter, it says he to reporters introduced main content, and that is how literally it comes across. But a good machine translation for that would be uh, there are possible translations, like he introduced reporters to the main contents of the statement is one. Second one is he briefed to reporters the main contents of the statement. It seems a little bit awkward, second one. Third one is he briefed reporters on the main contents of the last statement. That seems to make the most sense. And last one is probably the most probable phrase. So there are some literal translations that doesn't make much sense. And a meaningful translation, such as the last one, he briefed reporters on the main contents of the statement, is a more sensible one. And we would like a system to be able to produce a most meaningful one with a high probability. So there is one example. And okay, so what we're dealing with here is sequential data. We already talked about it. There was one whole chapter in our earlier discussion on machine learning or deep learning on RNNs or recurrent neural networks, where we unfolded a simple, feed-forward neural network over time, and said, okay, here is a way to handling a sequence of input data. And then we talked about how the basic, the core of the feed-forward network could be replaced by what's called as a LSTM or a GRU. So we've seen that before, and we're going to move beyond that in this discussion. So anyway, let's recapitulate that. And that natural language is sequential, and it is often regarded as a sequence of words rather than a sequence of characters or bytes. So we don't want to deal with them at the character level, A, B, C, Ds, etc. That is a sequence of characters. We kind of move beyond that and say it's a sequence of words. But you can see what happens when we move from sequence of characters to sequence of words. Characters are only, let's say, 26 possible alphabetical characters. And if we add all the special characters and symbols, maybe it makes it go from 26 maybe to 40 or 50 or so, maybe even 60 characters. So that's all. So the probabilities you need to work with are going to be only the probabilities associated with characters. But if you move to words, the number of possibilities become extremely large. So with characters, there are only 26 possible characters. With words, there are thousands or 10,000s or maybe 100,000. If you use all technical words and so on, we get into 100,000 and so on, like medical terms and so on. So the number of possibilities becomes very high. And so we refer to this as high dimensionality because the total number of words is very large. So word-based language models must operate on an extremely high dimensional and sparse discrete space. So this says the probability of words occurring one after the other is it may be zero, because some combinations will never occur if you have so many possible words, but other combinations are very possible. In ordinary language, we use certain words together. Those are all quite possible. But anyway, the word seems to be the best unit to work with rather than characters, which don't allow us to model meaning extremely well. So word, or it could also be phrases. So word seems to be a nice compromise between characters and phrases. So most of the work is all about modeling words. And so several strategies have been developed to make models of such a space efficient. So this is what most of the work is about words and about their occurrences. And so that's what we're going to be looking at. And so let's see, we just said that a language model defines a probability distribution over tokens in natural language. And what is a token? Is a word or a character or byte. You can define what a token is, and most of the successful language models. What do you mean by successful? People have been attempting these problems for a very long time of machine translation and trying to automatically understand what people are typing into a chat box, or Google is trying to figure out what you're asking when you're typing into their search box. So we need to interpret what is the most likely meaning of what you typed in. And the earliest models were based on fixed length sequences of tokens called n-grams. I mentioned this already, like bigrams and trigrams and so on. Usually we don't go beyond those, two words together and three words together. And so they were using these, we call them n-gram. N is however many words you're trying to model with probabilities. And to assign probabilities to sentences or sequence of words. So if you want to assign a probability to a sentence, like we just saw in the previous one on the Chinese translation, you want to say this is the most probable one. Well, can you assign a probability to that? How do you calculate that probability? Well, we could assign an n-gram based probability about pairwise or triple-wise, and somehow take those pairwise probabilities or triple-wise probabilities and uh, calculate from that the probability of that entire sentence. And so we are, of course, in a deep learning course interested in neural network language models. And so we talk about both the generic methods. So these are generic to any task, and they can be applied to natural language processing. These are generic to all neural networks. And there are also domain-specific methods. And these become specific to the domain. The domain is, of course, NLP. So we use both generic methods on very specific to natural language. So anyway, this is the overview of what is to come in our study of deep learning for natural language processing. So we begin with n-gram models, and we move on to very specific methods. And then, as I've mentioned before, we say n-gram have some, they work quite well, but we could do much better than that. And what are those better probability methods, and which leads us to these techniques of attention models and so on, and to current methods. Okay, so I'm going to move on to this is 12.4.0. This is just an overview. So that is just a preview. It says 12.4.0. O means that is just a beginning part. It didn't have any other real substance on it. So I'm going to move from that to the next topic. Let's see how I'm going to do this. So how's everyone doing? Screen sharing has stopped. Okay, I'm going to have to pull up my next one here. So this is all about n-grams is coming up next. Okay. So I need to screen share again. Wow, it even allows for, I could have done this on Facebook. Huh? I just clicked on a button here which says live on Facebook. Okay, live on YouTube. Wow, I didn't realize we could do all that. Yeah, we can try those kinds of things too. Let's see, share screen again. And I'm going to share screen. Okay. Let me take a pause here and see how you're all doing. Shreya, are you there?
Yes, sir, I'm here.
Yeah. Were you able to hear what I just spoke about?
Yeah, I could hear you well.
You can hear me well. Fantastic. Okay. You can
Yeah.
be my feedback person. Whether you're all able to hear this, and this is being recorded also. I'm just curious to see how many of you are here. Okay, there are quite a few. I see a picture of Jayant Priyadarshi. Hi, Jayant. Yeah. All right. Most of you don't have your video on here. You all have your audio. That's fine. It depends on. I think it doesn't affect my bandwidth. It might affect your own bandwidth whether you whether you want to have your video or not. But it's nice to look at the video occasionally to see who you are. Okay, very nice. Okay, so let's get back to Ngram models. And so we are now into topic of the first real topic within natural language processing. After we introduced in the overview, we just talked about natural language processing is all about probabilities. That's the main message of that part. And now we actually say, what is this Ngram model? And my first slide, okay, yeah, I highlight that here, Ngram models. My first slide again illustrates an example of probability in NLP. This is material from a company called, this is from the Allen Institute, one of the founders of Microsoft, Paul Allen. He went and invested a lot of money into an AI startup called OpenAI, I think. And this company has done some very interesting stuff on natural language processing. And so here are a couple of examples. The first one is from the Allen Institute, and they are asking the question here. Now I can barely read what is on that slide. Okay, I'm going to make it larger. Okay, that's better. And so what they're doing here is the sentence is the cat sat on the. All right, so you typed in the cat sat on the. And what could be the next word to predict the next word? And this is their program called GPT. We'll also talk about what is this GPT. It's also based on attention models, particularly something called a transformer attention model. And this probabilistic model is predicting the next word. The cat sat on the floor, on the bed, on the couch, on the ground, on the table, and on the sofa, on the edge, and the chair, and the desk, and the window. All right, those are all pretty reasonable answers, but you see what it takes there. You can't simply say cat sat on the, predict the next word. You can't simply say what's the word that comes after the. And of course, we got to take into account it's about a cat. Of course, a cat, is likely to sit on these kinds of places. It's probably, you won't say the cat sat on a plant, or maybe that's possible. I don't know. It is a certain possibilities that may not be there. And it's taking into account the fact that we're dealing with a cat here, and we're also dealing with the cat that is sitting. So we have so it is already exhibiting some knowledge of it's about a cat sitting and predicting most sensible answers to it. So we want a model like that, a language model that predicts a sensible next word. And the next example I give here is which is more probable. And one is all of a sudden I noticed three guys standing on the sidewalk. So there is a combination of words. All of a sudden I noticed three guys standing on the sidewalk. The same set of words in a different order is nonsensical. Supposing I take the same set of words, on, guys, all, I, off, notice, sidewalk, three, sudden, standing, the. All right, that will be, at least in English, this would be nonsensical. But actually, some of you familiar with some Indian languages, particularly Sanskrit. If I write a sentence in Sanskrit and I take the words and jumble them up, the meaning doesn't change much. That's a very interesting thing about the Sanskrit language. The way the verbs and the nouns are all written in a sentence, even if I change the order, the meaning doesn't change. I don't know if that's very universally true, but you can try out a few sentences and see what happens. It's not like in English. The order is extremely important. Maybe in other Indian languages too, its order is important. But Sanskrit is a unique language that way. All right. So anyway, this slide is not about Sanskrit. It's about probability, saying so we can give it a high probability. What is the next word? We can give a high probability to a sentence. And these guys at OpenAI, I'm just going off topic a bit. Actually, I have a slide on the topic on my slides about explainable AI and all kinds of things that are possible that in these open AI guys gave an example. They wrote one sentence which said uh, that uh, a team of scientists discovered in South America that there was a herd of unicorns which spoke perfect English. It's a nonsensical sentence that unicorns never really existed, and the unicorns that actually speak perfect English. But this system, language model system, was so good that it took that particular sentence and kept on generating new not only words but entire sentences, but an entire paragraph, just substantiating that nonsensical sentence that the scientists found that these unicorns were familiar with Shakespeare and all kinds of things went on and on and on, filling in a whole nonsensical story, which sounded like a very plausible write-up. It almost becomes believable. And this is what people talk about in this fake news, right? You can generate, you can start with some particular thing you want, and you can generate all kinds of perfectly logical words and sentences and so on. That's the power of this probabilistic natural language processing. Anyway, we're not going to go all the way there, but just to motivate you, because otherwise you might lose motivation saying, why are you talking about mathematics and probability here? So probability is important, and we are saying probability is essential in tasks with ambiguous output. Speech recognition, there you can quickly see why do you need probability is, as I'm speaking, I might not be articulating some letters or some words clearly, and you are guessing what I could have just said using probability. Spelling correction again, or grammatical error correction when you get options to change your writing based on spelling. Machine translation again, what could be the most meaningful translation? So all of this is once again motivating probability. All right, so I think we've motivated probability. So let's get on to how do you calculate probability then. So the next slide says computing the probability of a word. So we are stating it here as consider the task of computing probability of word W given some history H. And so how would you calculate the probability of a particular word given a history? Like the history is the cat sat on, let's say cat sat on, what is the next word? And we won't have a high probability for the as a high probability word and not some other word. So anyway, the probability of word W given some history H. And suppose the history H is, its water is so transparent that, all right. So we have got a history. Its water is so transparent that we want the probability that the next word is the. So how do we calculate the probability of the given its water is so transparent that? Well, okay, that could be done if we have a corpus, if we have a body of text, and we can estimate the probability from the frequency counts. So we count. So what is the probability of the given its water is so transparent that? Would be a ratio. The numerator is the count. Its water is so transparent that the divided by the count. Its water is so transparent that. All right, that's simple enough. Just run through your corpus, which is presumably quite a large body of text you have, and you can see wherever its water is so transparent that has occurred, and you say how often do you have the, so that would be the probability of that probability you're looking for, and so we can calculate that, and you can do it for every other possible word, which most of which won't occur in your text. Hopefully this sentence occurs somewhere and you can have a probability computed. But now comes the caveat, which says even the web is not big enough to estimate probability from frequency counts. So this says to calculate the probability, you have to look at the entire World Wide Web with, I don't know, billions or trillions of words of text. Even that may not be big enough to see how often do you get that phrase, its water is so transparent that the. So this way of calculating the probability directly is infeasible, even with all the text that has been generated ever. So a better method for these probabilities is to resort to a simple idea called chain rule of probability. So we invoke a simple idea which says that the probability P of x1 through xn, so these are n words, can be written as probability of x1 times probability of x2 given x1, probability of x3 given x1 and x2, probability of xn given x1, x2 through x1, xn minus 1, like that. So we can write it generally as the probability of a particular word given all the words that have previously occurred can be broken down like this. So where do we get this formula from? It is simply based on the product rule of probability, that how can I write probability of x1 comma x2? I can write it as probability of x1 times probability of x2 given x1. So it resorts to simple probability theory, and we go on from, well, you know how to write the probability of a pair of symbols or tokens or words. You can generalize it from 2 to 3 to 4 to 5, etc., and more generally in this way. So this says, applying it to words, probability of W1 through Wn, they were using some specific notation here. When you say W1n, it means W1, W2 through Wn. Can be written as probability of W1 times W2 given W1 and probability of W3 given W. Instead of writing again W1, W2, we are writing as W1, 2. So that is how it is saying. It shows the link between computing the joint probability of a sequence and computing the conditional probability of a word given its previous words. And they what this, so this is exact. There's nothing approximate here. We say you can always write that for any sequence, we can write it as a word, and then you look at the previous word and the previous two and so on. That can be done anyhow, and it'll give you the exact probability. That's not what we're after. We're looking for some other way, because even computing that in the previous slide, we saw even computing after all these words, the next word, the, is a pretty infeasible thing. So the intuition of the N-gram model is that instead of computing the probability of a word given its entire history, we can approximate the history by just a few last few words. This says we're going to get away from getting all the words that have occurred in the past, and that is where this idea comes in of N-gram, or in this case, Bigram we begin with. So it says Bigram. Instead of computing the probability, let's say here is another English sentence. Yeah, that's interesting. This is about Thoreau's, he's a famous philosopher, Thoreau, who was associated with Walden Pond, which is a pond in Massachusetts. It's a little lake there. And so this sentence says, Walden Pond's water is so transparent that, what's the next word? And, that's possibly the. It's so transparent that what's the probability of that? So we say, well, we can approximate it with the probability the given that. Oh, wow. We're saying forget about Walden's pond and water and transparent and all that. Can you just calculate the probability if the follows that? So we are making the assumption that Wn given W1 through n minus 1 is just Wn given Wn minus 1. So that is the idea of bigram probability, is just ignore all the previous words, just look at just the word before, and you have bigram. Well, that's going to be a drastic assumption where you are ignoring all the other context. But anyway, keeping all the, how often you're going to get Walden's pond is so transparent that in your in the World Wide Web, maybe you'll get it once or twice or thrice, but not many times. So you can actually calculate the probability of how often that happens, which is just a frequency count. And so so other extremity is ignore everything, just the previous one. An N-gram model says, let's go to, instead of just a previous one, let's do a few more. So an n-gram is a sequence of tokens, example words, and it defines the conditional probability of the nth token previous n minus 1 tokens. So this says instead of n, now we're saying it generally, not the previous 1 token, but look at previous 2 or previous 3 and so on. So for the nth token, it would be the previous n minus 1 tokens. And so the product of conditional distributions define probability of longer sequences. So now we can say the probability of x1 through x tau is written as probability of x1 through xn minus 1. And so we get into this bit of notation, t equal to n through tau, xt given xt minus n plus 1 through x tau minus 1. So this is again comes from the chain rule of probability. It says instead of just looking at the previous one, we can look at the previous two. If it's previous two, then you use chain rule now. How do you calculate previous two? The same rule which we just saw earlier on, it's being applied here. So now we have a distribution of P of x1 through xn minus 1 may be defined by a different model with a smaller value of n. So this is the idea that the probability can be approximated by a few previous words. Just the chain rule of probability. It's not much more complicated than that. All right. So the common things that people do are common n-grams or count how many times each possible n-gram occurs in the training set. So we'd have to look at that and some combination, water that would looking at the previous two and so on. So the models based on n-grams have been core building block of NLP. Oh, wow. N-grams have played an important role until the advent of deep learning. Deep learning is still a new topic, maybe 5 years old, at most maybe 7, 8 years old. What were people doing up to that point would be the n-grams played a very important role. And with n equal to 1 unigram, that is only look at the probability of the word. If I ask you what is the probability of the after all that, you would simply say, just pick the most probable word. Maybe the occurs a lot in English. So that would be not a very sensible way of putting a word in there. You might always be putting the for any guessing. Bigram seems to make more sense. So what has occurred just before, trigram is trying to be a bit more ambitious, saying look at previous 3. And here are some examples of n-grams. And I think I found it, maybe this comes from Wikipedia or something like that, where we have 4 grams and 3 grams on the table on the top. And if the first terms are your house is, uh, and the last term is great, it occurs 19 times. Your house is great. Or your house looks, the last term is dirty, then occurs only 3 times. Your house looks lovely, it occurs 13 times. Look, so these are referred to as 4 grams because we're looking at the previous 3. Your house is, your house looks, your house looks, your house looks, and then we are calculating how often, what is the next word. So this is what a 4 gram table would look like. A 3 gram table is we are just going, house looks clean, okay, 20. House looks dark, 6. House looks dirty, 13. So on. So these are all counts. And we can have a table of all these things of 4 grams and 3 grams. And that's an example. Apparently, this is a very powerful thing for the biological applications. I guess bioinformatics is a pretty big thing today, right? So for protein sequencing, for DNA sequencing, for computational linguistics, of course, we just, that's what we are doing largely here. At character level, we can do it. What is the next letter that's going to occur? And then computational linguistics at the level of word. And this table below, that's a Wikipedia table here. It gives you an example of protein sequencing, DNA sequencing. DNA sequencing involves all these base pairs, A, G, C, T, and so on. So we are looking at what is the probability of these letters occurring in a DNA sequence. And then we have 2 gram sequences. What's the probability of pairs and what's the probability of triples? And of course, we just saw examples of computational linguistics where we have words and so on. So these n-grams are pretty powerful and not only useful for natural language processing, but also in other areas. So you're trying to predict the next letter or next word and so on. So it is quite a powerful technique. But we're going to move beyond that here, saying we need more than just this. Let's see, here is some more interesting ones I found. And unigram and bigram probabilities. We have unigram counts, how often the word I occurs, 2533. Want occurs 927, two occurs 2417, eat 746, Chinese 158, food 1093, lunch 341, 278. Okay, so this is the kind of frequencies, unigram counts. How often do these words occur? Or you want to do bigram counts. How often do you get pairwise now? And you go and look in the in your corpus. How often do you have the pairwise want and eat and two and Chinese and so on? And you also have bigram count. You have bigram counts, or simply how often does you get this thing? How many times do you have food coming after Chinese? And we can convert those counts into probabilities. So there is bigram counts and bigram probabilities. So you would have to divide now all the counts by the total number of words in your body of text to get probabilities. And you can see bigram probabilities are all numbers between 0 and 1, extremely small. They all look like 0, 0, 0, 8, 3, and so on. So those are the probabilities of these bigrams. And if you know all these probabilities, and you want to now calculate the probability of a sentence saying, I want English food. And so you would look for, probability of I times probability of want given I, probability of English given want, probability of food given English, and then probability of food. And so from your bigram tables, you could get those probabilities. You multiply all those probabilities now, 0.25 times 0.33 times 0.0011. So when you multiply probabilities with each other, you end up with extremely small probabilities now, saying probability of that sentence is probably is 0.00031. So this is how it would work. You would calculate probabilities based on bigrams here. And so if you're going to be doing this, you would have to calculate all these probabilities and keep them in tables. And to train these n-gram models, we have to usually train both an n-gram model and an n-1 gram model, making it easy to compute. Probability of xt given all the previous n-1 possibilities is simply given by, how did you get this ratio? It is just based on the product rule of probability, and we are applying it. I think I have emphasized it early on. Product rule of probability. What is P of x comma y is equal to P of x times P of y given x, right? So that's the product rule, and we are applying it to a sequence repeatedly. So we would need a n-gram probability and an n-1 gram probability to deal with it. And so we'd have to look up the two stored probabilities, and we can calculate exactly to reproduce the inference. So we can calculate any conditional probability we want by storing all these tables of n-gram and n-1 gram in tables. Now it shows an example of trigram model computation. So if you had a sentence, the dog ran away, and so we calculate it by applying the same ideas we just discussed. The dog ran away is given by probability of the dog ran times the probability of dog ran away divided by dog ran. So this is just an application of these ideas of chain rule of probability. So trigrams can be used to calculate probability. Okay, and so then we come on to, well, if you can do it that way, what's wrong with this method? And so we have a limitation of these. These are called maximum likelihood methods of n-gram. Maximum likelihood simply says the most likelihood estimate of the probability is to divide the count by the using the count, right? How often? That's the maximum likelihood estimate. So Pn estimated from training samples is very likely to be 0 in many cases, even though the tuple may appear in the test set. So this can be, many of these probabilities are going to be 0. If it is 0 by 0, the ratio is undefined. We are looking through the tables to see how often does this occur. And when Pn minus 1 is non-zero, but Pn is 0, the log likelihood is minus infinity. So we got all these little mathematical problems that occur, that you got zeros in the numerator or the denominator, 0 by 0, or is the probability actually 0 divided by something? In which case the probability is 0, and we're going to be dealing with log likelihood. So we're going to try to take the logarithm of 0. Logarithm of 0 is minus infinity. So we can refer to this as numerical catastrophes. And so we can't really work directly with these kinds of probabilities, many of which are zeros or 0 by zeros. And so we need to use some kind of smoothing techniques. Previous one says shift probability mass to observed tuples to observe unobserved similar ones. So there are all kinds of techniques here. Add a non-zero mass to next symbol values, and or you can have a mixture of higher and lower n-grams, and what are called as Backoff methods, look up lower order n-grams. Well, we got to play around with all kinds of sophisticated methods now. We can simply add 1 to everything. That's the first one. Add non-zero mass to the next symbol values, and it can actually be justified. Even though it never occurs, you simply give it a 1. It is justified as Bayesian inference with a uniform or Dirichlet prior over count parameters. So simply adding 1 to every count avoids the 0 problem. That is a simple way of doing it. And the others are more sophisticated ways. And we use higher and lower order n-gram models, and they can be justified using nice mathematical arguments here. And there are nice papers just on this topic. What are you going to do with all these zeros? And say, why not use n-gram with Backoff? So NLP with bigrams or trigrams have been used for many years. So they have needed ways of dealing with these zeros. And for higher order models, like n equal to 5, wow, that's a quintogram or whatever, n equal to 5. Only a small fraction of n-grams appear in the training corpus, and it's a problem of data sparsity. We are talking about what is the probability of these 5 words occurring. Oh, those particular 5 words, they rarely occur. It's almost 0. And to counteract this, we use several Backoff techniques. And the most popular ones is being this particular formula, where we use some alpha and p are called Backoff coefficients and discounted probabilities. And I got a full paper reference here. So, of course, we are going to be arguing that n-grams are done with, and we're going to move on to better techniques. But there is a whole section we'll be talking about how can we take these deep learning methods which don't depend on n-grams, and we could combine it with n-grams, and maybe we can do even better. Maybe there is some value in these n-grams. So it is not completely written off, but that's the message we're heading towards here. Shortcomings of n-gram models, they're vulnerable to the curse of dimensionality. That is, as we go into higher values of n, it becomes sparser and sparser, and we need all kinds of tricks to get around it. And there are absolute Vn to the n possible n-grams, and V is large. V is the vocabulary. How many words are there in your vocabulary of English, or in your vocabulary of Kannada? I wonder how big the vocabulary of Kannada would be. English, I've heard 1,000 actually captures about 80% of language. Just 1,000 English words are enough vocabulary to capture 80% of English. 10,000 is needed for maybe 95% or something. But if you want to go on to talk about engineering and medicine and all, you're going to need 100,000 or something. So we are talking about n-grams to the power of that number you've chosen. So even with a massive training set, most n-grams will not occur. And one way to view a classical n-gram model is that it is performing nearest neighbor lookup. It can be viewed as a local non-parametric predictor similar to k nearest neighbors. So there are all kinds of tricks here for that also. And there is also another method called class-based language models. And instead of actually working with occurrences of words, why not think about word categories and use clustering algorithms to partition words into clusters based on their co-occurrence frequencies. And again, so there are all kinds of workarounds and techniques. So Ngram stuff is not to be dismissed easily. It's a pretty sophisticated method. It's a powerful method. It's a beginning point for probabilistic approaches. It works quite well, but the bottom line is still much information is lost in this process. So Ngrams did not solve all the problems that is needed for building very powerful systems like we see today in Alexa or Siri and today's NLP sophisticated methods, right? So we need to move on from there. Okay, that sets the preamble for the first two parts, and which brings us to the end of today's class, and we will be actually covering neural language models as the next topic, which might take us about most of 1 hour, and we could start on attention models also, but I think we're going to need 2 more lectures at this pace. I'm just trying 1 hour instead of 1.5 hours, and this is just an experiment to see how this is going to work. All right, so now let's see. I kind of left it to only me talking. I haven't figured out all the technology. There are ways of allowing you to send me chat messages and so on. So let me see. So Shreya, let me ask you, you become my moderator already. How did it go?
So it was really informative. I really enjoyed your class. It was the first of your classes that I've attended, and I took a lot from this session. So thank you. And
Okay.
I think the Zoom meeting went pretty well too. Like it was
Oh,
quite
okay,
smooth.
that's what I wanted to know. That's what I wanted to know. I know you're
Yeah.
not registered in the course, and I invited. By the way, for all of you, Shreya is an undergraduate at Ramaya College, and she's very interested in AI, and I invited her to join us, and she has become the moderator for the class. Fantastic. So
Yeah.
yeah, good. So you are my feedback. We can have an offline chat as to how we could improve this technology here. And I'm going to now see how the recording went. I need to stop the recording, and I don't know how to do that. All right, I need to figure that out. Okay, anyone else want to comment on the technology and questions, that kind of thing? Yeah. Go ahead and unmute yourself. Right. How did it go, guys? Were you able to hear me properly?
Yeah, I think it was great for me.
Okay. All right. Very good. And who's that speaking? Basil?
Yeah, Basil.
Basil. Okay. Very good. Very good. It was fine. I'm just curious where all you are. And I think most of you are no longer at Bangalore, right? And
Yeah,
Basil, where are you?
I'm in Delhi.
Delhi. Wow. Wow. You went back to Delhi, huh? Okay. Very good. Tell me, I'm just curious where all you are. Tell me, who else is from where? Yeah, when you unmuted, I think I can hear your street.
Hello, sir. I'm from Delhi too. Prateek here.
Oh, hi, Prateek. You went back to Delhi. Yeah. All
Yes,
right.
sir.
Very nice to have you. Okay, I'm glad you have an internet connection that allowed you to do this. Yeah, that's one of my worries, whether the students all have proper internet connections. And that's why we're not doing any quizzes and things like that online, because some of you may just not have the proper access. Okay. Who else is from where?
Hello, sir. I'm Dawal. I'm from Gujarat.
Where are you from?
Hello.
Yeah, that was
I'm
like
from Gujarat.
Gujarat, huh? You went back to Gujarat. All
Yeah.
right.
Yes,
Yeah.
sir.
Okay, very nice. Okay, so you have a good internet connection. All right. Who else is on?
I'm from Bangalore itself, sir.
All right. Bangalore is not the best because I am in Bangalore too. The internet connection keeps on giving up because I think there are too many people using the internet connection, and it probably gives up because of the load, Yeah.
There are too many people watching videos right now.
So many people watching videos. Yeah, I thought so. I think you might all be getting bored of watching videos. I said maybe you'll enjoy having a lecture. Most of the time, I'm having a hard time attracting you to my lecture. But maybe during this coronavirus time, the lecture may be more interesting than the usual things. You're getting bored at home. That's what I'm thinking. For me also, it's a good distraction to be giving you a lecture rather than watching a video or watching the coronavirus news morning till evening, right? I'm getting a bit nice to have a distraction from that. Yeah. All right. And then anyone else?
Sir, I am
Hello,
also
sir.
in
I am
Bangalore.
from Gujarat.
Where are you from?
I am also in Bangalore, Himanshu.
You're also in Bangalore. Okay. All right. Yeah. The connectivity has not been bad. I didn't get cut off today. Airtel did not disconnect my connection. Fortunately, yesterday it did several times. And so on. Today, yeah, I just thought that on a weekday it might be better than a weekend where everybody's free. Yeah. Now also everybody's
Even I
free.
am also using a Airtel.
Hmm. And where are you from?
Right now I'm in the campus.
Oh, you're on the campus. Yeah.
Yes, sir.
Actually, yeah, we have not been able to grade a few of the quizzes because the hard copies are on campus, and not everybody is going to campus. I think they're advising not to travel too much and so on. Okay, all right. Stay safe. Stay very safe. Okay, all of you again. Good to have you all, and we'll meet again. I'm going to send another message for Wednesday's class, and I'm going to put up this recording also if I can. It's going to be quite a high bandwidth, but I will try and put it up whether they allow it on Piazza or not. I don't know, and I will, or I have to upload it to some other place, and then maybe YouTube or something, and have it up there. Okay. All right, then. Look forward to having you back on Wednesday. Let the others know how it went, so that they can also join us in case other students can join. Again,
Sir, I had
Shreya,
a
thanks so
doubt.
much for being my primary feedback. Okay. All
So
right,
thank
then.
you, sir.
Yeah. Have a nice.
Sir, I had a
rest of-
doubt in today's class.
Yeah, yeah. Go
Like,
ahead. Go ahead. Ask.
yes, so you had told that this is a very old, like relatively older framework. So is it
Yeah.
being used right now? Like with the current technologies, current
Yeah.
frameworks that we have?
Yeah, all these things in AI, deep learning, they all developed over the years, and we are trying to find the best possible method. So after n-grams came deep learning. After deep learning came, how about deep learning and n-grams together? And okay, wow, that does better than simply deep learning. So it seemed like it was good. But then there has been a revolution in the last couple of years after these attention models came around, and particularly a particular method called BERT. So it's bidirectional transformer method. It seems like an absolute revolution, which doesn't use these n-gram ideas at all. And so, but I think in studying these methods, there is some value in building up little at a time. And we can say, well, do I need to study n-grams at all? Couldn't I be just studying, BERT? Of course, you can argue like that. But I think these are the basics. And you should remember that deep learning is largely about computing probabilities. So then you would ask the question, how do you calculate probabilities? What is being calculated here? So on. So these are the reasons to study the basics. And but today the most powerful methods don't seem to use this idea of calculating explicitly the n-gram, so on. So look forward
Yeah,
to
it's
more powerful
trivial
methods.
for me to understand this. Like it
What's
was
that?
very trivial. Uh, so I felt this was very trivial to calculate the probability of getting the next word. In the current times, the this might not work that well. So
Yeah, yeah.
that's
But
what, that's what I
they
thought.
used it for good things. You can predict, not just one word, but the sequences of words and so on. You can do a pretty good job with these bigrams and trigrams and so on. But not as powerful, because attention models, what they do is they're really keeping into account all that has been discussed before, long before, maybe in previous sentences, previous paragraphs, and all that. They summarize all that information. They're almost getting to human-like ability, saying, "Oh, okay, you said this earlier on. I'm going to use that to calculate what's happening." It's not just a syntactic thing. It is just the probability of these sequences of words happening. Something more about, the semantics of these words go together and so on. So that is what makes it the newer methods so much more powerful. All right. Yeah. Okay. That's that's a fair question. Value of these Ngram models, and I hope I answered it by saying, well, let's learn the basics first, and then go on to because what's going to happen is with the very latest method, they're pretty complicated models, and you lose intuition completely, saying, what are we computing? How does that work? So with this kind of a background, hopefully it makes you understand the next topics, the building block, right? Okay. Yeah. Any other questions? Okay then. So I will hope to have you all back on Wednesday again at 11 o'clock. So we'll stick to the IIC schedule, Monday, Wednesday. And if you all want technical guidance on implementing some of these things, I should ask some of my more proficient implementers to come along. Lokesh and Prasanna and Aditya and also Anirban. They might also join, so we could do that. And you can also send me email. Feel free to send me email if you want, if you have some issues there. Piazza also, what has happened is these technologies are all getting very sophisticated. Piazza has discovered that, oh, everybody is looking for online instruction, and they're making all kinds of tools available where we can have conversations and so on. We'll take this as an opportunity not only to learn the technical material, but also become proficient with these online tools. And at least for me, maybe you already are. For me, getting used to these tools is also one of my goals, is to how best to use this technology. All right. So we'll all jointly try and do this, and you can also send me suggestions about my improving my skills on this. Okay. Have a good day. All right. Bye now.
Thank you, sir.